Hello, everyone. This is lecture 3 of PTRE 575, well completions and advanced stimulation techniques. Last time, I hope I didn't go too fast. I felt like I was moving a little bit too fast. We went through some basic rock mechanic stuff. I said, in general, we are in the quest for a model that characterizes how the rock behaves. And when I say how the rock behaves, I mean stress versus deformation. Now, deformation, stress is very easy to quantify, right? In PSI. How much force I apply divided by the area of application is pounds per square inch absolute. Now, deformation is not easy to quantify. So we have a term called displacement, which sort of explains that. But then we have a dimensionless term that makes things easy, and it's called strain. Okay, it's dimensionless displacement. Is the displacement divided by the initial dimension. So if the material is 1 meter long, and then I apply a stress of X PSI, and I extend it to 110 centimeters, so it's 1.1 meter. The strain would be 1.1 minus 1 divided by 1, so it would be 0.1. Okay, dimensionless. That's one way, but that's the most simple example, okay? Hooke's law, basically. The thing is that the rock is 3D and it can deform in 3D. So you need to apply the Hooke's law in 3 dimensions. And this is exactly what you do in solid mechanics. All the equation in solid mechanics, those that they have terms like EI, Young modulus times moment of inertia, all those ugly equations which I hated when I was young, and I still do, to be honest. They do the same thing. They apply the Hooke's law in 3 dimensions, and it's the simplest model you can use to mechanically model, to characterize how does a solid behave mechanically. And when you hear the word mechanically, it means stress and strain, or stress and deformation in the way. Same thing. Strain and displacement is how you quantify deformation. And think about deformation as an English word, a qualitative term, whereas displacement and strain are mathematical terms. You know, they are math quantities. Now, we said that the rock behaves very much like a solid, but there are some key differences. And I gave you a picture that I took when I was working in the North New Mexico side of the Permian Basin, very, very east New Mexico, actually. And you see, it looks a lot like a solid. And we see some complexity in them, like calcite intrusions. It looks like an Oreo cookie. But ultimately, we want to apply these models that we learn in solid mechanics to rocks. And this is what you are doing in 465 geomechanics. Last time I showed you where the videos are for the last time I taught geomechanics. So if you think that you need to freshen up your memory, or if you took the class from somebody else and you want to see how I was teaching it, to get more grip on this stuff, you can go on my campus connection side and then click on I think it was fall 2024. Anyway, so 6 elastic moduli can do the trick for us. So if we have 6 elastic moduli, I can describe exactly how the solid material behaves. But the situation is much easier than that. I don't need all 6. I don't need to quantify all 6. You give me 2, I give you the other 4. So that's good. And there was a homework in geomechanics when I was teaching the class where I was asking the students to build a spreadsheet using these equations. And basically, you give 2 and you get the other 4. So you have all 6, basically. Unfortunately, the rocks don't behave fully linearly elastic. I mean, they're fairly anisotropic and heterogeneous. That means several properties change in value as I change direction, and also as I change region. When I change direction and the values change, we call that anisotropy. Okay, when you see the word an in Greek, an is like the it's like the English unresponsive means not responsive, same thing. Aniso means unequal. Unequal. Okay, iso means equal. Aniso means not equal. So the property changes in direction. So when you hear anisotropy, automatically think of direction. When you hear heterogeneity, think of region or location. I go from here, and I see different values. But anisotropy means that I'm just looking in a different direction and I see different values. It's like the room has different color walls versus this room having blue color walls, and then the other room having green, and then the other room they are having red and yellow down. They are not the same thing. Some people say that anisotropy is a type of heterogeneity, but this is not really true. Anyway, then we started adding complexity to the model. So we started from where you guys finished with solid mechanics. And let's just say in geomechanics, you took that, you applied it on Earth, it became geomechanics, right? Now we take it one step further and we add pores on the rock, like this thing is porous. It's a sponge to erase the stuff on the board, but it's porous. I don't want to, if I blow air on it, it's gonna make a whole mess. But ultimately, fluid can get in and enter those pores and stay there. This is how the rocks are. Now, the fluid in those pores is under pressure. We call that pore pressure. Now, if I create a situation where the pore pressure, the pressure in the pores is uneven, and the pores are connected, fluid will start trying to move from the high pressure pores to the low pressure pores. And this movement can affect the size of the pores. The bigger the pressure of the fluid inside the pores, the bigger the pore will be. This change in the shape of the pores, the size of the shape, and sometimes the shape, is what we call pore elasticity. The walls of the pores are elastic. They change size. Mathematically, trying to incorporate this is very, very complicated. People do PhDs and publish books on this topic, volumes of books on this topic. The mathematics of that is terrible, very, very complicated. The amount of poroelasticity that we apply in our classes is very, very minor. Is what we call colloquially, not very official term, linear poroelasticity. And it's like a very, very simplified model, which is after Terzaghi approximation, 1942, using the Biot's poroelasticity which is a theory from the year earlier, 1941. We are gonna see a little bit of that but it's not. It's nowhere near the complexity that people see when they do research. Even if you try to talk to people who do computational modeling, like we have a project with Itasca Consulting Group, which is a company in Minneapolis, owned by University of Minnesota, that creates software and used in geomechanics. Very famous one called FLAG 3D, fast Lagrange analysis of continua, which is like a very, it's a, I don't want to call it inhumane software, but it's very hard to deal with. But very powerful when used properly. I have a student working on that. Anyway, highly complicated stuff. And this is something that, unfortunately, poroelasticity, petroleum engineers are affected by poroelasticity. Civil engineers and mining engineers, almost nothing. When I did my postdoc in civil engineering for 1 year, I was doing stability of tunnel intersections, which is very similar to the way a perforation tunnel intersects a wellbore. I remember I was trying to talk to my advisor about poroelasticity. He was like, don't worry, he said, in civil engineering, you don't need to worry about poroelasticity. I was like, oh, very nice. I took everything out. It made the mathematics 3-fold times easier, honestly. Anyway, and the main thing about poroelasticity is that it's very dynamic. It's affected by time. And it's very difficult to incorporate time in those mathematical models. Okay. Now, we talk about how the rock behaves as a rock, as an element of the rock. Like you apply stress, it deforms. And you compress, it becomes smaller, you extend, it becomes, you apply tension, and it extends. Now, let's do something. Well, we did that last time. We took this element of rock and we put it in the subsurface under a lot of rock. So it had a lot of rock above it and a lot of rock on the side and below it. Okay, this rock was applying stresses on it. This stress wasn't from the element itself. If I take this element of rock and bring it to the surface, no stress would be applied. But if I take it and put it in the subsurface, you will have stress applied from its top and from its side. Okay, from its top you have what we call the overburden stress, and on the side you are going to have what we call horizontal confinement or tectonic confinement or just confinement. Yeah. But in general, the element would be subjected to 3 compressive stresses that are mutually orthogonal. And when I said mutually orthogonal, I think I did this and I said, look, the index finger is at right angle from the thumb, and the thumb is at right angle from the middle finger, and the middle finger is at right angle from the index finger. They are all at 19-degree angles from each other. And this is the situation here. You have S1, S2, and S3. Now, 1, 2, and 3, the number, will depend on the quantity, magnitude. So the most compressive of all will have the most positive value, and it will be assigned S1. The smallest, least compressive will be S3, and the intermediate will be S2. Unlike what you learn in solid mechanics, where they made tensile stresses positive, because in all other disciplines of engineering, you get tensile stresses more than compressive. Compressive stresses are a rarity. In the Earth's subsurface, it's the opposite. You get more compressive stresses than tensile stresses. And even then, petroleum engineering is a little bit of the exception, where petroleum engineering is the very few times, deals with the very few times where you get tensile stresses. You don't see a lot of tension in the Earth subsurface. So to make our life easier, we go the other way. So when you use models like the one I mentioned earlier, FLAG 3D, you need to remember that for them, tension is positive, compression is negative. So don't forget to, we spend a lot of time trying to figure out whether we made a mistake or is the stuff that the way we put them in the model wrong, and we're getting the wrong answer. But anyway, S1, S2, S3. Now, it doesn't mean that S1 will be vertical. It could be horizontal. And also, it doesn't mean that those, the mutually orthogonal, doesn't mean that it has to be this way. It can be this way. It can be that way. It can be that way. It doesn't mean that I drew them like that. It doesn't mean that it's like that. But yeah. Now, if I want to incorporate the effect of pore pressure is acting in every direction, as we learned in geomechanics. So I just need to do one thing, and that is subtract pore pressure from every what we call principal stress. Okay, every one of those S1, you subtract pore pressure, it becomes sigma 1. S2 becomes sigma 2. S3, sigma 3. And the S1 would be in the direction of sigma 1, or the sigma 1 would be in the direction of S1. S2, sigma 2 would be in the direction of S2, sigma 3 in the direction of S3. So I change their values, but I don't change their relative rank. So they still stay the same. And that is assuming pore pressure that is a solid with static pore pressure. And what I mean by static pore pressure is that fluid in the pores is not moving. So I have pore pressure, I don't have pore elasticity. Okay, I don't have fluid movement in the pores. The pore size doesn't change, stays as it is. No fluid is moving inside the pores. Just stays static. Okay, I modeled that by just subtracting pore pressure. Okay. Where was I? Okay, now I think this is where we stayed last time. We finished last time. Now, okay, as I said earlier, it's not always like this. Sometimes it's like this. Sometimes it's like that. Sometimes it's like that. Sometimes it's like that. Okay, it's not always a nice, easy way of. They are not aligned a certain way. The stresses. Okay, so if I really want to characterize mathematically the stress field, I don't need 3 values. I need 9 values. I need a tensor. Okay, which has normal stresses with cyan color, the blue color, light blue color, and then I have shear stresses that are the orange color. Shear stresses are a little bit complex. Okay, it's a stress applied in one direction. It's a stress load in one direction triggered by a stress load applied in a different direction. Okay, it's how do you call it? It's not indirect loading. It's more complex. It's more of a it's a stress in a plane J applied triggered by stress on plane I. Okay, very, it's not a direct stress. So Those complicate our model mathematically, okay? But we can fix that. Because frame of reference matters, okay? There is a way. I cannot change. If the stresses of the Earth are like this, I cannot change that, okay? It's going to be like that. What I can do to help myself being mathematically comfortable is that I will change my frame of reference. I will change the way I'm looking at the problem to make the problem easier for me, mathematically speaking. Okay? We do that a lot when it comes to the mathematical manipulation for geomechanics. We do that a lot. So, frame of reference matters. There is a way I can look, I can apply my frame of reference a certain way that would make all the orange shear stresses go away. Okay? Think about it. Nicolas Espinosa, my original advisor, and he's a professor in Texas of for geomechanics, and his videos are online. He has a cube, a transparent cube. He colored one side blue, the other side yellow, red, the other side green. And he puts it under white light and then moves it in front of you. Okay, if you move that cube, you're going to see all the colors of the spectrum. Okay, all the possible colors of the spectrum are going to be visible. But there is a position that you can align that cube from the way that you are seeing it, that you are going to be seeing it as red, white, red, green, and blue. Okay, in that case, that would be what we call the principal frame of reference. What you see, the red, blue, and green are the principal stresses, okay? If all the orange shear stresses become zero, what you have in the middle, you know, as you are rotating that cube, the whole tensor, all the values, all 9 values are changing. All 9 values are changing value, okay? Until you get that perfect direction, perfect alignment, where all the orange values are zero, and the blue values, what remains that called the principal values, is going to be the principal stresses. We'll call that 1P, 2P, 3P, the principal stress. Bear in mind, a common mistake by students that I don't want to see in the exam, I hate seeing it, is that they say, oh, you know, I give you this, and I tell you, give me the principal stresses. And what they do is they take this, and they say, oh, and they write it here. No, this is not the same. I'm joking. But this is not the same thing. You need to rotate not the model, but the way you are looking at the model, so that you get every shear stress to go to zero, and then the middle ones to become 1P, 2P, 3P. This is done mathematically by computing the eigenvalues of the matrix. I had another professor, he was a mathematician. He used to say the eigenvalues of a matrix is like the ID value, the identity of a matrix. Okay, so if you find the eigenvalues, you will have the principal stresses. And how do you find the directions of those principal stresses? Is the eigenvectors. Finding the eigenvalues is easier than finding the eigenvectors. But yeah, ultimately, once you do that, it's very easy to do that for the effective stresses. Okay, once you have, also bear in mind, never subtract pole pressure from a shear stress and say that this is the effective shear stress. Okay, when we subtract, we subtract from the principal stresses. So you subtract pore pressure from S1P, S2P, S3P, and you get sigma 3P, sigma 2P, sigma 3P in this case. You don't do the shear stresses. The shear stresses are a little bit very different processing that they need. Goes beyond the scope of that class. So, example problem number 1. Solve for the in situ principal stresses and directions of a stress field given by tensor S. Now, one thing about, and I hope that you are not scared, and you shouldn't be by now, is that in geomechanics we have a lot of math, but the good thing is that it's going to be easy math compared to what could have been. For stability reasons, in the Earth subsurface, if you want a stable stress state, you are going to have something that is diagonally, it's going to be diagonally symmetric. So if I take a mirror and I put it here, what I see on this side, I see on this side, right? So I'm diagonally symmetric. This is good. It makes my math easier, okay? If it's not diagonally symmetric, it means that I have an unstable stress state. So it's something that won't be stable in the long run. It might be the case right now I have some sort of motion, some sort of rotation, something is moving, and I have this. It's a very temporary stress state. It's not gonna be, but in general, if you get a non-diagonally symmetric matrix, means that something is going on. Pinch yourself. Either somebody is making a prank at you, or you made a mistake somewhere and you got that. It's unlikely, impossible in your line of work, unless you are a seismologist looking at stresses, very quantitative seismologists. Even you want to see how the stresses change during the earthquake or something, then you may do like tectonic movements and stuff like that. I don't think in geomechanics, what we are learning in this class, you won't care about. Any matrix tensor, any stress tensor that you are gonna see will have to be diagonally symmetric. Anyway, how do I solve for the eigenvalues? And the answer is, I set the what we call the characteristic equation of the matrix equal to 0. That is the determinant of S minus lambda I. Lambda is a constant that has fixed value. I is the identity matrix, all zeros except the diagonal, which is 1. And S is the vector that is given. So this is what basically means in matrix form, what I just said in matrix form. S minus lambda times the identity matrix. Now, I expect that you know how to do the determinant, but the idea is that once you have the matrix, you take, let me use blue. You take this and you multiply by these two minus these two. Then you do minus, you take this, you multiply by this, subtract by this, and then, oops, you take the last one, you multiply by this, subtract by this, and so on and so forth. Okay, this is how you do the determinant. Because of what I said earlier, the kind of matrices you are gonna see in geomechanics are not too terrible, okay? I know in your linear algebra classes or like differential equations, no, before that, multivariable calculus, which I had to take as a freshman as soon as I came to the US first semester, you see much harder matrices than this, what you're gonna see here. So we do it, we end up with an algebraic equation and we solve for lambda. Now lambda will have 3 values. Why will it have 3 values? Because there is 3 stresses, right? 3 stresses mutually orthogonal. So 3 values of lambda. Lambda 1, lambda 2, lambda 3. In this case, lambda equals to 1, 2, and 4. Okay, so lambda 1 will be 4, because that's the most compressive. Lambda 2 would be 2, and lambda 3 would be 1. Okay, easy. Nothing terrible. Okay. Now the harder part, eigenvectors. Okay, now if I want to find the direction of those, every eigenvalue, the stress is acting in a direction, right? In a certain direction. We call that, so I need to find a vector. Vector has 3 values. So for every lambda, I get a vector that has 3 values. Okay, now I'm getting a little bit more complicated, but it's not going to be too terrible either. I apply that lambda, I get a new matrix, which is S minus lambda I for each lambda, multiplied by the V matrix, Vi, Vj, Vk, the 3 components of the eigenvector, equal to 0. I apply lambda equals to 4, and then I get 3 equations. From those equations, I get minus 3Vi equals 0, minus Vj minus Vk equal to 0, minus Vk minus Vj minus Vk equal to 0. So what I see here is something very common in linear algebra that I forget off the top of my head how they call it. Those are the same. So I get rid of one and I'm stuck with the other one. So what I have now is 2 sort of broad equalities for the vector that I'm looking. That Vi is equal to 0 and Vj is equal to minus Vk. Okay, this is not enough. It doesn't give me the 3 values I want to. It just tells me that this value is 0. And then it tells me that this value is minus Vj. Or in the way I wrote it, actually, it just tells me that this value is minus Vk. So it's like I have my V is 0 minus Vk plus Vk. Okay? So I get an infinite amount of vectors that can satisfy this, right? Because it can be this, right? 0, 1, minus 1, 1. It can be 0, minus 2, 2. It can be 0, minus 3, 3, right? All those are valid. I get an infinite value of vectors. And some people will struggle to find the logic now. Let me tell you something. What I'm looking for is a vector that points to the direction I'm looking. This stress is acting. Okay? This vector is acting in a certain direction, right? And it's this much vector. Okay? Now, this vector altogether is still acting, pointing in the same direction, right? It's just a bigger vector, but it's still pointing in the same direction. I can be infinite long and still point at the same direction. So it doesn't really matter how long the vector is. I'm just pointing at the same, as long as I'm pointing at the correct direction, I get infinite possible values. Now, by convention, to make our life easier, and this is what I expect you to do during an exam, if you get a question like that, is that what I'm expecting you to give is the unit magnitude, like a vector of unit magnitude in the correct direction. So you will say you take this vector and you divide by the magnitude of the vector, you get a unit vector in that direction. Okay, so what is it? What is the magnitude? The magnitude of vector v is 0 plus minus 1 plus minus, come on, sorry about that, plus minus 1 square plus 1 square, square root. What is it? Square root of 2. So the unit vector would be, basically, it would be 0 divided by square root of 2 minus 1 divided by square root of 2, 1 square root of 2. Okay? Now, let's do it for the 2. So the unit vector, the magnitude of 2 is 0 square plus minus 2 square plus 2 square is what? 4 and 4, 8. Square root of 8 is what? Square root of 4 times square root of 2. So 2 square root of 2, right? If I'm not mistaken. So now the unit vector of v would be what? 0 divided by 2 square root of 2 minus 2 divided by 2 square root of 2, comma 2 divided by 2 square root of 2. So the 2 cancels out. And what I have is the same as before. 0 minus 1 over square root of 2 plus 1 over square root of 2. Right? It all goes back to the same value if I do the unit quantity. So it doesn't matter what you chose for Vj or Vk. You choose one, you get the other. Whatever you choose, if you divide by the magnitude of the vector, say that you do 3, okay? Sorry, guys. Oh. Is 0 plus minus 3 square plus 3 square. What is it? 9 and 9, 18. 18 is the square root of 9, square root of 2, so 3 square root of 2. Now, what will become now? It's going to be v 0 divided by 3 square root of 2, comma minus 3 divided by 3 square root of 2, comma 3 divided by 3 square root of 2. 3 cancels out. And you get, again, 0, obviously. 0 divided by 3 square root of 2 is 0, obviously. You get 0, comma minus 1 divided by square root of 2, comma 1 divided by square root of 2. You always end up at the same answer if you divide by the magnitude. So if you give me your answer as a unit vector, you will be all giving me the same answer. Okay, so we call that free choice. Okay, free choice. You choose your favorite number, and then as long as it's not 0, because 0, 0, 0 is not a vector. It doesn't point into any direction. Yeah, that's basically what we did, what I showed you in the previous slide. Any questions? before I make things easier. And I don't show you here, but the same thing, you need to do the same procedure for the other two values. Lambda equals 1 and lambda equals 2. And there is several software that can do it for you, but of course, in the exam, in the heat of the battle, you have to do it by hand. This is not really a math class, so don't expect to get too overwhelmed with math. But you need to know how to do those stuff. And probably you already know from geomechanics. Okay, if there is no questions, I assume that you have seen that before and you are comfortable. I have office hours tomorrow, but I will have to close them early because I have an engineering faculty meeting and then a department faculty meeting. So I need to do that. But anyway, I'm available and the TA is available as well by email. Anyway, you can reach out to me. Please do if you have any questions. Now, let me make things a little bit easier because, you know, geologists, and we are not geologists, but geologists in general, they don't like math. And there was one of them that said, let me make it easier for you, for all of us. How about I say in the earth, for the stresses, for the depths that we are looking for, that we care about, petroleum engineers and other people, let me just simplify this. Instead of doing all this stupid math to arrive to the, let's just say that everywhere, one of the stresses, one of the principal stresses is vertical, and the other two are horizontal. So he simplified it. His name was Anderson. E.M. Anderson from England, 1904. He said, for the stresses that we are looking for, 1951, many people cite, I don't know if it's this, it's really 1904 when the theory came out. I think in 1951 there was a book that I think he wrote, even though it was 40 years later. But anyway, so he said, let's just say one of those stresses, it doesn't have to be S1. One of those two, S1, S2, S3, well, S1P, S2P, S3P is vertical, perfectly vertical, and the other two are horizontal. And he gave exceptions. There are exceptions to this. If you are near a salt dome, for instance, the stresses tend to follow the shape of the salt dome. And there are some other exceptions. But in general, for the depths that we are interested at, let's just say that one of the three stresses is perfectly vertical, and the other two are horizontal. So that's one rule. One of them is vertical to horizontal. The second rule is that we will call the horizontal that is more compressive than the other horizontal SH max. Notice capital H, uppercase H. And the other one, we'll call it SH mean. Okay? SH max will always be bigger, more compressive than the SH mean. By the way, what time does the class end? I think it started at 12:30, so it must be ending at 1:45, so we still have time. You know, at this stage of the semester, students are still excited, so they gather up outside of the class and wait until I finish to go in. And but eventually, you know, the enthusiasm will die. But I don't see anybody outside. And I was wondering but yeah, we still have time. Good. So, and also notice lowercase h for SHB. Okay. SH max is always bigger than SH mean. You can have them equal to each other, then it would be one stress, basically one value, but you cannot have SH mean ever being more compressive than the SH max, okay? If it's more compressive, automatically that one should be SH max, okay? Whichever of the two is more compressive is assigned the symbol SH max, okay? Now, if I subtract the pore pressure, it's going to be the effective value. It's going to become sigma H max and sigma H mean. Now, the vertical one would be called SV or SVert. Same thing. SV, that would be the vertical. Now, SV can be bigger than SH max. SV can be smaller than SH max. SV can be smaller than SH minimum. Okay? Anyway, you want. But you cannot have SH mean bigger, smaller, bigger than SH max ever. The only rule, there is only two rules. One of the stresses is aligned with the vertical, and the other one is that SH max is bigger than SH mean. Those are the two rules of Anderson. That simplifies our mathematics a lot this way. Because the human mind is, remember I said that if the stresses are aligned this way, I just need to change the way I'm looking at stuff. I need to look at it like this, and then things become easier. So I change my frame of reference. Human mind is, human nature is adapted to looking at the most simple frame of reference, which is vertical, horizontal, they don't like angles, okay? It makes things infinitely more simple by applying Anderson's theory. Very, very simple. And we can have a case where we don't have an Andersonian stress field, but in that case, yeah, mathematically it's going to be more involved. But yeah, if you are in a place where you can apply Anderson's faulting theory, things become much easier. Okay. Now, we have three permutations that are possible. Now, we said SV can be bigger than SH max. And by definition, it's going to be bigger than SH mean. And then I'm having a normal faulting stress state, what we call a normal faulting stress state. And a very common example of this, look, I have a typos in my slides. I forgot to update. Gulf of America. I was laughing with students last year when I was doing advanced reading. I had to change all the slides to Gulf of America from Gulf of Mexico. I thought I did, but apparently not in this class. Because I guess I somehow missed that. But yeah, the Gulf Coast is normal faulting. Let's see, what else is normal faulting? Permian Basin in Texas is normal faulting. The Williston Basin is also normal faulting, weak normal faulting, but it is normal faulting. It's a very common stress field, okay? SV is the most compressive, and then SH max, and then SH mean. Then I have reverse faulting or thrust faulting. One example of that is the east coast of the US, okay? Reverse faulting and thrust faulting, you have it when you have orogeny, which is a term that you probably learned in geology, comes from the Greek word oros, which means mountain. Okay, oros means mountain, mount actually. Like Mount Everest is Oros Everest. This is what creates the activity that creates a reverse faulting stress state is what eventually builds mountains. It's plates coming together and lifting things up, expanding things upwards. Reverse faulting. So near Nepal, those areas, you will see a lot of reverse faulting. Australia, even others. Nepal, New Zealand, some parts of Argentina, all reverse faulting. So in that case, SH max is bigger than SH mean, which is bigger than SV. And then I have strike slip faulting. The west coast of America is very common. A very common strike slip faulting. Strike slip fault is San Andreas fault. You can remember that one. That's when SV is in the middle. So SH max is the more compressive, SH mean is the least compressive, SV is in the middle. Okay, strike slip faulting is more complex in a sense that you have two types of that. The right lateral and the left lateral, we're going to talk about it. Right lateral is called dextral. And that's the modern Greek word for right is dexia. That's why dextral. And the left lateral is sinistral, which is the ancient Greek word for left. Okay. Okay. So one way to understand how these faults work is by those two plates cut. You can take a piece of wood and cut it at home and then use plates like that. When I was a student in geomechanics, the professor who cut wood for us colored it a different color, and he brought it and gave it to us. But you can do it. All my students in this class are online, so I cannot do that. But ultimately, it's the same thing. You have two pieces of wood cut diagonally. Together, they merge perfectly. Okay. One looks like a shoe. Okay. I'm going to call that the foot wall. And the other one is going to be called the hanging wall. For this analysis, so that we are easy on ourselves, our own simplicity, let's just say the foot wall stays as is. Doesn't move, okay? Only think of the hanging wall moving. Even though the foot wall can move too, just think of the hanging wall only, okay? All right, for the normal faulting, what is the most compressive? Is the SV. What is the least compressive? Is the SH mean. So if the stress applied from the top is the heaviest, and the stress on the horizontal is the least, and then you have SH max is in the middle, it doesn't really make a difference. SH max is like this. Forget about that. It doesn't cause any motion. The motion is between the blue and the green. So the SV is stronger, the SH mean is the weaker. How do you expect the hanging wall to move? The answer is that the hanging wall will move down, okay, in this direction. So it's gonna move like this because I'm pushing it from the top in the hardest way. So that would be the motion expected to be triggered by normal fault. Okay, all the faults are gonna be in that sort of more or less motion. In reverse faulting, I have the opposite. The least compressive is the SV, and the most compressive is from the side SH max, right? SH mean is in the middle. It's gonna be the red one, doesn't really matter. So SH mean is it doesn't matter. SH max is the stronger. SV is the weak. So how do you expect the motion, the hanging wall to move if the footwall stays stationary? I will expect, by the way, the footwall in this case is this, not this. So I'm expecting the hanging wall to move up. So I have something like this motion. You understand how this motion creates mountains? Things move upwards, right? The hanging wall moves upwards. This is the motion that creates mountains, right? Okay. Now, the difficult one, strike slip. Strike slip, SH max is my stronger. SV, sorry, SH mean is my weaker. Can understand my handwriting. SV is middle, doesn't matter. So what I have now is that I'm like this. And I'm pushing it in a way that it's gonna move like this. Okay? Now, we said two types earlier. We said dextral and sinistral. We said dextral, sorry. Dextral, right. Sinistral, left. Okay, so dextral is the kind of strike slip fault where if I sit on any of the plate, imagine if I'm here, standing here, where do I see the other plate moving? I see it moving to my right. Now, imagine if I am here. Where do I see the other plate moving? To my right again. Right? I see both plates. It doesn't matter where I stand. I see the other plate moving on my right. That's how the San Andreas fault is. It's a dextral, right lateral strike slip fault. The opposite would be sinistral. Okay, I cannot think of a left lateral right now off the top of my head, but there are some. Yeah. So two types of strike slip: dextral and lateral, and sinistral. Reverse or thrust fault. Sometimes we hear thrust faults. It's the same thing. And then normal faulting, like Gulf of America. Anyway, let me erase everything. I think I had one more point to make here. Visualization with the footwall and the hanging wall. Okay, we said that. Any questions? I believe these are things you have already seen before. And you need to be comfortable with. If not, you should be made comfortable with. So now, let me try to make things even simpler than that, even simpler than Anderson. Because geology is like simplicity, I guess. Mathematical simplicity. They are complicated on other stuff, but they are easy on their own stuff, you know? You know, in the oil field, you always get arguments between the engineers and the geologists, and the geologists are always complex. They're like, oh, you know, it's not like this, it's like this. So anyway, we'll make it even simpler than that. How about we collapse all those three values into one? So instead of SV, SH max, SH min, three values, let me take those three values and make them one. Okay? And we will call this term A phi. Simpson, 1997, developed this term A phi, which varies from 0 to 3 to describe a given stress state using all the combination of the three values. Okay, forget about the pore pressure in this case. Just use the principal stresses, not the effective ones. SV, SH max, SH min, S1, S2, S3, and put everything together into one value. And this is the equation you are going to use. It looks complicated, but it's not. Okay, you have four unknowns, four variables, S1, S2, S3, which you know how to handle. For normal faulting, SV is S1, SH max is S2, SH min is S3. For strike slip faulting, S1 is SH max, S2 is SV, and SH min is S3. And for reverse faulting, S1 is SH max, S2 is SH min, and SV is S3. Easy. And then you have another unknown, not unknown variable called N. N for normal faulting is 0, for strike slip faulting is 1, for reverse faulting is 2. And then if you put the values, you're going to get a value ranging from 0 to 3, okay, for alpha phi, A phi, okay? From 0 to 1 is normal faulting, from 1 to 2 is strike slip, from 2 to 3 is reverse, okay? So one value to characterize the stress state in this direction. So for instance, if I tell you Williston Basin has A phi equals to, I think, 0.98. You're going to say, it's normal faulting because it's from 0 to 1, but it's very close to strike slip because it's close to 1, which is between normal faulting and strike slip. So this is how I give you one value, and automatically you understand what I'm trying to say. Beautiful. So you apply this equation, and then you come up to this range from 0 to 3. And then there was somebody, an excellent fellow from Stanford, who said, let me take this A phi spectrum from 0 to 3, apply temperature colors on it. Blue for 0, dark blue for 0, dark red for 3, everything else in between. So green will be 1.5. And I will color them up according to the stresses. So where I have blue is normal faulting, where I have green is strike slip, where I have red is reverse faulting, and I have all the color spectrum in between. And he got his PhD in 2020 from Stanford. Then he started working in USGS, and recently moved to Fervo, which is a geothermal company based in Golden. I took a road trip for Christmas or after, in the first days of this year. I left on January 2 from Grand Forks, and I got back in January 11 or something, January 12. We had lunch. We met for lunch in Golden. His name is Jens Erik Lonsny. He's from New Zealand. Very, very smart guy. Very, very smart guy. And I think he's 1 year older than me. He must be born in 88 or I was born in 89. Yeah, very, 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 very good person. We met. His maps are excellent, and he's also doing some plots that are very, very useful, actually. And yeah, he works in he's a geomechanicist for Fervo now. And we had him to give us talk 2 years ago. No, 2024, fall of 2024. And during the Q&A of his talk for ARMA, it was virtual, via Zoom. We asked him some questions and gave him some ideas, and he actually is working on those ideas still. So he did not regret giving a talk to UND, actually. Because when we met, he showed me some calculations he's making, and it's very similar to some that my students are doing, and they are using his plots, etc., etc. And he was always nice, I have to say, in our publications. If we want to use any of his maps, he is very, very graciously giving us permission to do so. Like, very nice guy, always helpful. Whatever we need him, he helps. And I might have him give a talk to AEE, the Association of Energy Engineers, whatever it's called. Since he's working for geothermal now, I will tell Dr. Alamuti to have him in mind, bring him over if they have, if they are looking for new speakers. But yeah, Jens Erik is a very smart guy. He changed his last name for a while to Lundstern, so you may see some publication under that name, but now he's back to his original. And he has a website which you can use to calculate a fee, but you are better than that. You know better. You can calculate. You can make a simple calculation yourself. It's not hard to calculate a fee. Okay, a few more minutes. So, shifting gears a little bit, we talked about externally applied stresses, right? SV, SH max, SH min, or S1, S2, S3, same thing. They apply stresses on the element from the outside. But what about the deformation that I'm causing, okay? The relationship between stress applied and deformation caused, etc., that we talked about at the beginning of this lecture and last lecture are known as constitutive relations. So when you're in a conference and you present a poster and somebody tries to be smart at you and say, what constitutive model are you using? He's basically asking, okay, what model am I using? Is it linearly elastic? Yes, no, maybe something more complicated, like a more Coulomb model or a Hagen-Brown model that some people are using. Or what we use is linearly elastic fracture mechanics, which is based on linear elasticity with some modifications to include the fracture, to account for the fracture. But yeah, constitutive relationships always think about stress deformation or stress strain. Always think of that when you see the word constitutive. And constitutive model, yeah, linear elasticity, etc., etc. So a block height H cross-sectional area A, I apply stress on it, I pull it somehow, don't ask me how, but I apply a force Fz by pulling it down, and it will elongate by an amount delta Z, like this. I get the extra delta Z. Here, apply force Fz, force F in the direction Z, across cross-sectional area A, and I got the elongation delta Z from the initial height H. Okay, I arrange those in a mathematical fashion, and I have Fz normalized by A, because remember, force divided by applied stress is force divided by the area of application. And then I have delta Z divided by the initial value. Together, delta Z divided by H is actually strain, right? Is what I mentioned earlier. Deviation divided by the initial value. The change divided by the initial value is dimensionless. Strain. Stress. The constant of proportionality will be what we call E. And E is the Young's modulus. E is a measure of the stiffness of the material. Now, if I ask you what are the units of stress, you're going to say something like PSI, Pascal, whatever. So pressure dimensions. And then what are the units of strain? We said dimensionless. So what would be the units of E, the Young's modulus? It's going to be PSI divided by nothing, or Pascal divided by nothing. It's going to be pressure units. Okay, so that's a measure of the stiffness of the material. Okay, steel behaves like a linearly elastic material, so it has a Young modulus, and so does rocks. But which do you expect to have the highest Young's modulus? The answer would be steel, because steel is stiffer. So it would have a higher Young modulus. It means to get the same amount of deformation, the same strain, I need to apply a bigger stress. Okay, than a rock, for instance, or wood, or something else that is linearly elastic. It is measured using a UCS test, which we're going to talk in a later module. I believe it's going to be module 3. Okay, that's it for today. The students are coming in for the next class, so we'll carry on Wednesday, on Thursday. And remember, office hours have tomorrow may be cut short because of the meeting that I have, but feel free to reach out to me in any way. Thank you very much. Have a nice evening, and I'll see you all on Thursday.
Well, thank you, Professor.
Thank you, Samuel. Good to see you again. And thank you, Donald and Michael.
Have a good day.